Awesome. Thank you very much, Marcel. Yeah, it's a great pleasure for us to be here today and to present our awesome tool SMAC, despite this being after the lunch break. So I hope you're somewhat awake at least, and there'll also be a hands-on session as part of this, right? So you'll have some time to also work on this a little bit yourself. Good, then let's get started. A little bit about us first, because Marcel was too lazy to do that. No, I'm kidding. So my name is Alexander Tornede. I'm a postdoc in the group of Bernarius at Leibniz University Hanover. Did my PhD with Professor Eike Hüllemeyer in Paderborn on algorithm selection before that. Right now I'm working on interactive and explainable automated machine learning. I'm head of the SMAC development team actually. Of course, also a member of the AutoML supergroup as part of Marius' team. Yeah, my background is in computer science, and besides doing research and basically being kind of consumed by our job, as probably most of you, I love to play board games with friends and do some things outside. Good.
Yeah. Hi everyone, I'm Carolin Benjamins. I'm still in the PhD phase, and I'm also at the Leibniz University with Marius. And I'm a member of the SMAC dev team. I've looked into the episodes of SMAC and into all corners. And my focus is general on AutoML, dynamic algorithm configuration, and Bayesian optimization. And I also like robotics and contextual reinforcement learning. And in general, I love automation and making complex algorithms more accessible. So SMAC is perfect for that, I would say.
Wonderful. Then let's get started with today's game plan. So what will we be doing in the next 1.5 hours? We'll give you a short introduction into SMAC. What is SMAC? What can it do? Maybe what can it not do in the next 20 to 25 minutes. Then we'll have a hands-on session with actually a Colab notebook, so you don't have to install something yourself. Everything is set up there. We'll go quickly through that with you, so then you have some time to work on that yourself, and we'll be available for questions or if you have any troubles. And then we will close with a short wrap-up where we discuss a little bit what you have learned maybe, and you can also share your experience and maybe what you think could be improved both on SMAC and on this session itself. Good. Quick recap of hyperparameter optimization, right? Because it's after lunch and maybe some of you are not super familiar with the topic yet. For those of you who are, well, then you can just maybe relax a couple of more minutes. In hyperparameter optimization, our goal is really to find the best performing configuration, which is here this lambda star, right? And it's best performing in the sense that we think that it should minimize the cost function C, which you can see here, right? And the C, in our case, in machine learning, is usually just a loss function, usually on the validation data, right? So basically this calligraphic edge. And then what most hyperparameter optimization tools do, they work in kind of an iterative fashion, where the optimizer here proposes a configuration, and this configuration is plugged into the target algorithm. The target algorithm is evaluated. So we basically get feedback of the configuration according to our cost function in the optimizer, and the optimizer does something clever with this feedback, and then hopefully suggests the next configuration that is either better or that it can at least learn something from, right? The most common scheme, or a very common scheme, I would say, is Bayesian optimization here. And since actually there was supposed to be a talk on Bayesian optimization before this, we added these couple of slides here to make sure that we're all on the same page here, right? In Bayesian optimization, the idea is really to exactly have this sequential or this iterative group in a very special form. Namely, we're studying with a so-called initial design. That is essentially just a process that gives you a set of initial configurations that you can evaluate. For example, like a snowball or random sampling, you can really do anything there. The idea is really that you have something that you can then train your surrogate model initially on. And the surrogate model here is one of the two main components of the Bayesian optimization loop. This kind of bluish part here, right? The aim of the surrogate model is really to kind of give us an idea on how the optimization landscape, the loss landscape, really looks like that we're trying to navigate, right? And then this initial design is basically evaluated, you plug those points into the surrogate model, and you have your first model that gives you some idea of how this space looks. And then the two components that really interplay here are the acquisition function of the surrogate model, and the task of the acquisition function is basically to give us an idea for any point in our configuration space and how valuable would that point be to evaluate, right? And ideally, this acquisition function gives us this exploration-exploitation trade-off, where we want to have a point maybe that tells us something new about some parts of the landscape that we don't know really yet, but it's also not really detrimental, and ideally even better than the configurations we have seen so far, right? So essentially, it really suggests a new configuration here for our surrogate model, and this configuration is then evaluated such that ideally we lose uncertainty about the space at exactly the point that we evaluate that. Right, and then we evaluate that, feed that back into the surrogate model, and yeah, update that. Good. With that being said, so now we'll basically really talk about SMAC and not just some basics that are maybe helpful to understand. In particular, we'll talk about SMAC3, so the current version that we have right now, which is implemented in Python. And we actually recently, like half a year ago or something, released SMAC3 2.0 with really some awesome new features. We've rewritten lots of stuff. So yeah, I think it's a really nice tool. Good. What are the features? So what can SMAC really do for you? First of all, it is open source, and we actively maintain it with actually, I think, quite a considerable team. So I just really make sure that we invest quite some time into that, and I think that really pays off. SMAC can deal with quite rich search spaces that basically have floats, ordinals, categorical variables, and also conditionals. So you can really say this hyperparameter should be in this range, if another hyperparameter is on that value, and those kind of things. So you can really configure things that you will see in practice. So that's really nice. It offers you an ask and tell interface, which is quite nice if you don't want to follow the really standard optimization loop, but I don't know, maybe for your use case you want to do something in between evaluating configurations or something, so you can really customize this loop with this ask and tell interface. And I think there's lots of use cases you can really do with that are maybe not so easy to do with other tools. We support the continuation and also warm starting optimization. So basically, if you have some configurations lying around, you can warm start our tool with that. But also if you have stopped one run because, I don't know, maybe it crashed or something, you can actually continue from there once you have fixed the error. So I think that's really nice features for practical usage. We offer several intensification mechanisms that allow to efficiently compare configurations, especially in situations where you have multiple seeds and maybe even multiple instances or multiple data sets. That's also something that isn't supported by every tool, right? And for those of you who have been standing or seen the prior band poster over here, right? So we also support user price to a certain extent in SMAC right now. Of course, we also support parallelization, and we can do that both locally, but also on a cluster, featuring the Dust library. So that comes in quite handy when you really want to parallelize largely. We also, of course, support multi-fidelity optimization when you really have multi-fidelities that you want to evaluate your tool on, and you want to speed up that process quite a lot. Of course, we also support multi-objective optimization, and we have explicitly implemented ParEgo for that. So if you want to go with multiple objectives, you can also do that. We also support the optimization across many tasks. This is kind of what I said, where I said we support multiple instances. For example, this is quite common in algorithm configuration. And what's also quite handy, I think, is that the function you want to optimize can either really be a Python function, so Pythonic, but you can also just optimize the script. And that's quite handy, especially when your target algorithm isn't implemented in Python, but maybe some C script, and you have a bash script that you can use to run that. We can handle that, so that's really nice. And we're also easily extensible with callbacks, so even if you want to use that for your own research, feel free to do that, right? You can just write your own callback, plug that in, and do lots of stuff with that. For example, we are currently doing several optimized stopping criteria with that. Helena actually is doing over there, is doing that. And all of that is done via callbacks, so you really have some flexibility to do that. Good, and with that, I hand over to Carolin.
Thank you. I can actually use this mouse, perfect. So now let's take a tiny look how SMAC actually works and how SMAC is built. So we have a modular design where we can combine the individual components as we like. And we also have some presets, which I will show you later on. But everything starts with a scenario where we define our target function, so the thing we actually want to optimize, where we define our configuration space, the budget, and maybe we even have instances. So this is the start of everything in SMAC. And depending on what kind of scenario we have, what we want to optimize, we have different presets, different facades. And they configure all those components in the middle. So we have different initial designs, for example, random design, Latin Hypercube or Sobo. We have different surrogate models, random forests and GPs. We have different intensification methods, and of course, different acquisition functions. And what is also nice, we decoupled the sequential model-based optimization loop from the actual target function evaluation, so we can do everything in parallel. So let's take a closer look into the facades, and yeah, let's start with the classic scenario of black box optimization. So here we have the scenario, we have a function. Of course, we don't know how this function looks like. We can only query it. We want to find the minimum of that, and that's classic black box. So we can select this facade, and for this we pre-configured a Sobol design. We use a Gaussian process as a surrogate model, and we use EI as an acquisition function. Another common scenario is combined algorithm selection and hyperparameter optimization, or structured hyperparameter optimization, where we can have actually conditionals. For example, if we have different algorithms with different sub-search spaces, we can actually model that and express that with SMAC and optimize that. And that's the classic facade hyperparameter optimization facade. Also uses a Sobol design, but uses a random forest as a surrogate model, and also different acquisition function. And of course, we have more scenarios or more facades. For example, if we have an expensive task like deep learning, if we want to train a neural network, and where we can have different fidelities, that means we can stop the neural network training earlier than we normally do to get an idea of the final performance. We can use that in the optimization process to evaluate many configurations with a small budget, and then later select configurations which we want to evaluate on a full budget. And this is also preset, which is the multi-fidelity facade with a random initial design, also random forest as a surrogate model. And here we have the intensification method hyperband, maybe you know it, and also a certain acquisition function. And last but not least, we have algorithm configuration, where we want to find a configuration performing well on a set of instances. So not only on one function we want to optimize, but on different instances. Here we have the default initial design, a special random forest, which is able to handle instances. And we have aggressive racing as an intensification method, and also log EI as an acquisition function. So most of the times, if you have an optimization problem, it maybe falls in one of those categories, and then you can start, then you can use those presets and see whether it works for you already, without needing to configure every component in detail, which you of course also can do. And yeah, as I said, facades are only shortcuts, so they are presets. And with this, it's probably too small to read, but we will put the slides up. So you have different dimensions on how to configure your optimization, for example, different budgets, different dimensions. What should you do if you have instances? What should you do if you have noise in the objective function? If you want parallelism, how do you configure SMAC then? Or if you can use fidelities or multi-objective. And this graphic helps you to find an entry point where you can configure stuff in SMAC. And last but not least, we also have a sweet comparison to other packages, I think from 21, which we also saw yesterday already. And we can see that SMAC is able to handle loads of different scenarios, and it's also easily extensible. And we also use SMAC for our own research. And we also have some exemplary results from the paper, where the main insights are that usually before people used GPs as a surrogate model, but random forests for black box HPO can outperform other approaches with TPE and GP models. And the other insight is our version of WOP, also with random forest as a surrogate model, has also very strong anytime performance. So SMAC is powerful for different scenarios and with different combinations. And this already leads us to the hands-on session. And we've prepared a little link for you, a tiny URL, and just follow this URL and you will find the Colab notebook. And how do we do it? Do you want to introduce?
Yeah, just go quickly through it.
Yes.
So yeah, it's best if you just go there and then actually create a copy of the notebook, because of course it's private, you won't be able to edit it. But if you create your own copy of the notebook, then you can of course also play around with that. and that's the whole point. I'll give you a couple of minutes to go there, and then I will quickly go through the page. Okay, well, maybe while we're waiting, I can already show you some parts of the notebook, and then you can go through that on your own again. So the first block is really about installing all the dependencies you need. The only important thing is really that after you've run the cell, just restart the runtime, because otherwise you will run into problems. So exactly, just restart the runtime, but the notebook also says so. Well, then we will basically just have a small example to validate the installation, just to make sure that everything works for you. You will have some code on basically how to do a classical training pipeline that we can then later use to actually optimize things, right? We'll be setting up a search space together. So this is already in a guided form. You can go through this, and hopefully it's more or less self-explanatory. And if not, we'll be around. So just raise your hand. Right, some search space, and that goes on actually with properly defining this training function to be able to actually be able to train based on a given configuration. We'll basically show you how you can model conditional hyperparameters, so something that I think is quite important in practice. All of this is basically based on an MLP here. Then we will define once again a complete pipeline and really a class that you can then optimize. And then after that, with all of the stuff that we've defined before, we will set up SMAC, including a scenario, go through that, and then also show you how you can do multi-fidelity optimization with SMAC. And then at the later part, basically, there are some more features. If you manage to get through the whole notebook on time, of course, feel free to try some things yourself, right? You can replace the pipeline with something you want to optimize yourself, things like that. Just play around with it a little bit, try to get a feeling for how this works, and then if you have any questions, we are, of course, around. All right, everyone. So it seems the coffee break is already being prepared outside, so that means that it's time to wrap up here. So what did we, or hopefully you, learn today? You've seen how you can actually perform hyperparameter optimization with our very nice tool SMAC. SMAC is highly modularized, offering many customization options, for example, via the Ask and Tell interface, or via callbacks, lots of others. But at the same time, we also have the nice facades like Carol presented that really make the usage for standard use cases easy, hopefully, and that really allows you to apply this without like reading the manual for 3 hours. Since we are open source, we of course welcome collaborations, contributions. I mentioned that we are, I think, quite a large team, but of course we also have lots of other stuff to do during our time, right? So it's quite natural that there are some issues which maybe we cannot allocate time yet to, or maybe never. But of course,
don't find ourselves.
Exactly, or don't fire ourselves. So if you find a problem, feel free to raise a bug on GitHub. If you have any question, also just raise an issue on GitHub. That really also helps us to see where maybe the documentation needs to be updated. And of course, you're also free to fix stuff yourself, add new features yourself. That's really awesome. Lots of QR codes over here. And before we end, there's a little sneak peek. So if you want to actually know what happens inside SMAC during the optimization, you can actually download on the very left. You have this the directory sign in Colab. And, if you run it on your computer, you just have it in your file structure. You can actually download the SMAC output and put that into our visualization tool, which is called DeepCave. It's also freely available, and that gives you a little insight about the optimization run actually. So what happened internally. So for example, right now we have here, wonderful. You can see that basically you can load several runs here. I selected a run to load here that was predefined. Then you can take a look, for example, at the configuration footprint really. Yeah, so how does the configuration landscape look like? What kind of configuration do you evaluate? What is the cost over time? So how did this actually change when you ran it longer? This is some accuracy that we define here, that we optimize, right? So this is how it goes. We also support lots of other things like parallel coordinate plots, and the cool thing is that this is actually plotly, right? So you can also actually select things here to visualize stuff, really see, for example, what hyperparameters here lead to certain results, and I think that is quite helpful. And of course, if you see something here, then maybe tell me how, because I don't. But you can also do basically XML stuff, so explainability stuff, like you can compute hyperparameter importance values, like either local or global, using different methods, and then just see, what did we find while optimizing the hyperparameters as kind of byproducts, also to understand what happens. And also something that's really nice, partial dependence plots, to really see what's going on. So yeah, we support quite some things there. If you want to know what's going on, try to install that. It's not too complicated. You can just input the output of SMAC there and really learn something about what happened during the optimization. Good. Wonderful. With that, I would like to actually highlight the SMAC team itself again. And some of the SMAC team members are actually here today. For example, Eddie over there, he actually contributed the code base. Helena's over here. And we have Leona over here, Caro, of course. Marius, of course, also actually he did the first commit on SMAC3, which was actually a couple of months ago. That was, what was it, the 10th or the 5th birthday? The 10th?
No, that's not true.
8th birthday. So yeah, Marius was really the one doing the first commit there. And of course, we have lots of other people. We have Zara, who's also working on the SMAC team. We have Tim, who's also working on the SMAC team, right? And Zara and Tim are also working on the Deep Cave team. Yeah, did I miss anyone? Defun, right? Defun is also working on the SMAC team. So basically, almost everyone's working at least to some degree on SMAC from our team. So yeah, huge shout out to them, because without them, I think none of this would exist today. Good.